Welcome to AI Paper Slop. Today we are looking at HRM-Text, efficient pre-training beyond scaling by Wang et al. Over at Sapient Intelligence and MIT.
Yeah, and this paper is genuinely wild. Imagine beating a massive, multi-billion parameter model from Meta or Google, but you don't use a giant server farm. You do it with the compute budget of, like, a high-end gaming PC.
Right, because this paper outlines a 1 billion parameter model that was trained from scratch on just 40 billion unique tokens.
Exactly, and the total compute budget was literally $1,500.
$1,500. That is just 1.9 days on 16 H100 GPUs.
Yeah, it's microscopic, yet it performs competitively with massive open models like Llama 3.23b, Qwen 3.52b, and Gemma 3.4b.
Which is insane. How is that even possible?
Well, it manages this by completely throwing out the standard playbook. You know, standard AI development relies on autoregressive pre-training.
Right, the brute force approach.
Exactly. Forcing a model to predict the next word across trillions of tokens of raw internet text. But this paper completely abandons that dogma. Instead, the researchers combine a hierarchical recurrent model architecture with a strict task completion training objective.
So if you are an ML engineer fighting for cluster allocations right now, you definitely want to pay close attention to this.
Oh, absolutely. This paper proves that targeted structural priors and focused training objectives can actually replace immense parameter counts. You really do not need a massive compute cluster to do meaningful foundational AI research.
I mean, we are talking about 100 to 900 times fewer training tokens here.
Yeah, and roughly 96 to exactly no feedback loop at all. But the hierarchical recurrent model, or HRM, changes that completely. The architecture actually draws inspiration from biological systems.
Like the human brain.
Yeah, specifically the functional organization of the frontoparietal loop. Yeah, the brain doesn't process complex reasoning in a single, strictly feed-forward sweep. It decouples computation into distinct timescales.
Okay, so how does the HRM mimic that?
By splitting the architecture into a slow-evolving strategic layer, which they call the H module, and a fast-evolving execution layer, the L module.
Oh, interesting.
Yeah, so you start with an initial state derived from your input embeddings. Then the model executes 2 high-level H cycles. And inside each of those slow H cycles, it runs 3 fast L module updates.
So it's kind of like a software engineering team building an application?
How do you mean?
Well, think of the H module like your senior system architect. They establish the high-level system architecture, the strategic context, the overall goal.
Right. And that vision evolves slowly.
Exactly. Meanwhile, the L module is like the junior developer. They are iterating rapidly, writing the specific functions, debugging local errors, and, executing the granular details within that broader architectural vision.
That's a great analogy. The senior engineer maintains the stable semantic context so the project doesn't drift, while the junior developer performs the local iterative refinement.
But wait, recurrent networks aren't exactly new?
No, not at all.
The field relied on RNNs and LSTMs long before the transformer took over. So if simply adding a loop to a transformer architecture is so incredibly effective, there has to be a reason the entire industry abandoned loops for feed-forward layers.
Right, and that reason is gradient instability. When you train a recurrent model, you have to use backpropagation through time.
Where you are unrolling the loop and passing gradients backward.
Exactly, through the exact same parameters over and over again. And in modern deep learning architectures, looping the same parameters creates a massive headache around normalization layers.
Right, because of the normalization trade-off.
Yeah, which makes recurrent language modeling nearly impossible to scale. First, you have post-norm, where the normalization sits outside the residual branch.
Okay, and what does that do?
It cleanly bounds the forward activation variance. It keeps the numbers from exploding as you loop forward.
That sounds like a good thing.
It is for the forward pass, but it places a mathematical roadblock directly on the main gradient path. If you loop post-norm, your error signals vanish into nothingness before they can reach the earlier steps.
Ah, so your backward pass just dies.
Exactly. The alternative is pre-norm. That's where you place the normalization inside the residual branch, leaving the main pathway completely untouched.
Which gives you a clean identity path for gradients to flow backward.
Right, so the backward pass survives. But on the forward pass, you are accumulating unnormalized residuals step after step.
Oh, I see. So if you loop pre-norm, your hidden state variance grows unboundedly.
Yeah, the representations blow up, the numbers go to infinity, and the model just collapses. So post-norm kills the backward pass, and pre-norm kills the forward pass.
That sounds like a nightmare to optimize. How did they fix it?
They introduced MagicNorm. It exploits the asymmetry between the forward pass and the backward pass.
MagicNorm. Okay, how does that work?
Well, in MagicNorm, each recurrent module is built with multiple internal prenorm blocks. But crucially, the entire recurrent module is capped with one final normalization layer at the very exit.
Sitting directly on the main pathway.
Exactly.
Wait, so if there is a final norm at the exit, you are essentially trapping the variance before it escapes into the next sequence of operations.
Right, which bounds the forward activation variance, acting exactly like post-norm. It keeps the forward pass stable.
But doesn't that just recreate the vanishing gradient problem on the way back? I mean, the error signal still has to push through that restrictive final cap.
It would if you unrolled the entire loop all the way back to the beginning during optimization. But this is where truncated backpropagation through time changes the math.
Oh, so they cut the horizon short.
Exactly. On the backward pass, the gradient horizon is truncated. Instead of tracking the error back through 50 steps of the loop, the algorithm only looks at the last few recurrent steps.
So the error signal only has to pass through that restrictive final norm a very small number of times.
You got it. And within that short truncated horizon, the gradient gets to flow freely through all those clean, internal, pre-norm identity connections.
Wow. So during optimization, it behaves like a stable pre-norm architecture. That solves the fundamental trade-off completely.
It really does. You get the forward stability of post-norm and the backward gradient flow of pre-norm.
But even with MagicNorm trapping the variance, unrolling a loop for language modeling at the very beginning of training when the weights are completely random, that sounds incredibly volatile.
Oh, it is extremely volatile at initialization. So the paper pairs MagicNorm with a warm-up deep credit assignment strategy.
Warm-up deep credit assignment.
Yeah. Early in training, the gradients only flow through the very last two recurrent steps. K equals 2. You don't ask the optimizer to navigate a deep pathological sequence of random weights right out of the gate.
That makes sense. It only optimizes the final two operations.
Right. And as training progresses and the model stabilizes, they linearly warm up that gradient horizon. They gradually extend it backward until the optimizer is updating the last 5 steps of the loop.
It kind of mirrors how you would teach a complex physical skill, you know?
How so?
Like you don't ask a beginner to execute a 10-step gymnastics routine perfectly on day 1. You teach them the final dismount first.
Oh, yeah, definitely.
Once they master those last 2 steps, you add the flip before it, expanding the horizon only after the foundation is actually stable.
That is a perfect analogy. And the paper backs this up with fascinating mechanistic evidence regarding Jacobian products.
What did the Jacobians show?
Well, if you look at standard deep backpropagation through time, you typically see massive log-normal gradient spikes. Because when you multiply the same weight matrix by itself repeatedly across a loop, it's like compounding interest.
So certain directions in the vector space either vanish to 0 or amplify exponentially.
Exactly, which creates heavy-tailed gradient distributions that just destroy the training run. But MagicNorm, combined with that warm-up schedule, physically smooths out that distribution.
It suppresses the catastrophic spikes.
Yeah, and keeps the median gradient magnitude healthy.
Okay, so the architecture is stable. But even with a perfectly stable recurrent loop, if you feed a tiny 1 billion parameter model the sheer unfiltered chaos of Reddit and random Wikipedia articles, it is going to drown.
Oh, completely. It does not have the parameter count to memorize the entire internet.
Right. To hit that $1,500 compute budget, fixing the architecture was only half the battle. They had to radically rethink the model's diet and how they penalized its mistakes.
Because the current dogma demands that you spend massive amounts of compute forcing the model to predict raw text just to build a general world model.
Like feeding in a web page, and it spends compute cycles trying to predict the formatting tags.
Or the typos, or the exact phrasing of some subjective blog post, yeah? An enormous percentage of your FLOP budget is wasted predicting prompt-like or task-irrelevant text that has nothing to do with actual reasoning.
So how did they get around that?
HRM-Text skips raw text pre-training entirely. They use a task completion objective.
Okay, what does that look like in practice?
The model is pre-trained from scratch exclusively on instruction response pairs. And they compute the negative log likelihood loss solely on the response, conditioned on the instruction.
Wait, so the model is never penalized for failing to guess the exact wording of the human's prompt?
Never. It is only judged on the accuracy and quality of this answer.
That is brilliant. Every single parameter update is concentrated entirely on generating task completions rather than wasting compute reconstructing the query itself.
Exactly. And because they aren't asking the model to predict the instruction, they can change the attention mechanism.
Oh, really? How so?
Well, standard large language models use causal masking for everything. Token 5 can only see the tokens that came before it. Token 5 cannot see token 6.
Even if both tokens are part of the initial prompt that the user has already provided.
Right. But PrefixLM masking changes this. All the instruction tokens attend to each other bidirectionally, exactly like an encoder model.
So the model gets to see the whole prompt at once.
Yes, it understands the full context simultaneously, and then it switches to standard causal generation, predicting one word at a time for writing the actual response.
What does that physically do inside the model?
It leads to higher attention softmax entropy. See, in standard causal masking, the attention distribution tends to be very local.
Because it's hyperfixating on the immediately preceding words to guess what comes next.
Exactly. But with PrefixLM, the attention maps show a much flatter, broader distribution.
Meaning higher softmax entropy.
Right. The model's attention is spread evenly across the entire prompt. It makes much broader global use of the context because it already knows the whole instruction.
Okay, but let me play devil's advocate for a second.
Go for it.
If the model never reads a normal article start to finish and is never trained on the raw text of the internet, the obvious critique is that it becomes a hollow shell. Like, a model trained strictly to answer specific instructions might completely lack foundational world knowledge.
That is the exact concern, which brings us directly to the training mixture and the benchmarks. They build a dataset of 40 billion unique tokens and train for about 60 billion tokens total.
Which, for context, models like Llama 3 are trained on 15 trillion tokens. So a 40 billion token diet is microscopic.
It is. So the diet relies heavily on high-quality synthetic data, math, and textbook reasoning. They utilize datasets like FOLLN, SYNth, and OpenMath Instruct2.
Datasets that are dense with logical deductions and step-by-step problem solving.
Exactly. But the researchers made a profound, almost philosophical decision during the data preprocessing.
What did they do?
Well, the current trend of the industry is to rely on explicit chain-of-thought reasoning, right? You prompt the model to generate its thought process inside think tags before giving the final answer.
Yeah, that's everywhere right now.
The researchers explicitly stripped all text inside think tags from their reasoning datasets.
Yeah. Wait.
They deleted it all.
But if OpenAI's O1 model proved that explicit tokenized chain of thought is the current meta for high-level reasoning, hiding the reasoning steps seems entirely counterproductive. By deleting those thinking steps, aren't they removing the exact data that teaches the model how to solve complex problems?
You would think so. But if you give a standard transformer explicit tokenized chain of thought, it offloads the computation to the output stream. It uses the generated tokens as a scratch pad.
Because its internal feed-forward layers are shallow?
Exactly. But this HRM model is not shallow. It has a recurrent brain. By stripping those tags, the researchers forced the model to rely on its internal hierarchical recurrence.
Oh, wow.
The model must use its slow H modules and fast L modules to figure out the complex logical steps internally in its latent space before it outputs a single word of the final answer.
So they are denying it a scratch pad to force the internal loop to do the heavy lifting.
Yes, they built a recurrent reasoning engine and then deliberately starved it of explicit step-by-step text to force the engine to actually turn over.
That is incredible. And does it work?
The performance payoff is staggering. This 1 billion parameter model, trained for under 2 days, hits 84.5% on GSM-8K and 56.2% on math.
Those are massive numbers for a 1 billion parameter model.
It comprehensively beats FLOP-matched standard and loop transformers across the board. It is putting up highly competitive numbers against models like Olmo 3.7b and Gemma 3.4b.
Models which require hundreds of times more training data and compute.
Exactly.
But what about the hollow shell critique? How does it fare on general knowledge versus pure reasoning? Because if you strip away the raw internet, you assume it loses trivia capacity.
The benchmarks reflect exactly that trade-off. Broad factual knowledge, measured by MMLU, is highly sensitive to scale and raw data volume. The model scores a 60.7% on MMLU.
Okay, so that's respectable for a 1 billion parameter model, but it's not industry leading.
Right. However, reasoning and execution benchmarks, like math and GSM-8K, benefit massively from the recurrent architecture and the task completion objective. The model is definitively a reasoning engine first, and an encyclopedia second.
Are we sure it didn't just memorize the math problems, though?
They checked that. The researchers ran strict anagram contamination tests. They verified that these massive scores on math and GSM-8K are not a result of the models simply memorizing the training data. The reasoning capabilities are genuine and generalized.
Okay, so the performance proves that the loops work. But we need to look at how the model physically utilizes its parameters differently than a standard transformer to achieve this density.
Yeah, if we are claiming it does latent reasoning in its hidden layers, we need proof that the deeper recurrent loops are actively changing the model's computations.
How do they prove that?
They used an effective depth analysis. They employed a mechanistic interpretability technique called the Logit lens.
The Logit lens. That allows you to take the hidden state of the model at any intermediate layer and project it through the final output vocabulary head early, right?
Exactly. You are essentially asking the model at, say, layer 4, if you had to guess the next word right now based purely on your current internal state, what would it be?
And then you measure the KL divergence, the statistical difference between that early guess and the model's absolute final output at the end of the network.
Right. And think of a standard transformer like a massive printing press. Once the first few shallow layers set the metal letters into place, the rest of the deep layers are mostly just pressing the ink onto the page. The meaning doesn't change much.
So when you apply the Logit lens to a standard transformer, the output distributions stabilize very early.
Exactly. The early layers guess the word, and the deep layers just refine the statistical confidence of that same guess. They don't actively change the final answer.
But I'm guessing the HRM is different.
Oh, completely. In the hierarchical recurrent model, the Logit lens reveals a completely different dynamic. The KL divergence remains large, even in the deeper recurrent layers.
Interesting.
The model is like a sculptor working with clay. It does not just lock in an early guess. Layer by layer, loop by loop, it is actively using its recurrent depth to meaningfully change its mind, alter its internal representations, and reshape the final output.
So it is genuinely using the full allotted depth of the loop to process the information. That is fascinating.
And because the model processes information through this iterative loop structure, the researchers discovered they could exploit the architecture for a massive performance hack at inference time.
A performance hack? What kind of hack?
They call it auto-guidance. During the forward pass of a recurrent model, the hidden states from the shallow recurrent loops are already sitting there in the GPU memory. They were computed as a necessary part of the sequence.
Okay, so you have them readily available.
Right. And because you have the intermediate answer from loop 1 and the refined answer from loop 2, you can mathematically interpolate or extrapolate the logits from different recursion depths.
Oh, I see. So if loop 1 pushes the probability of a specific token to 40%, and loop 2 refines it and pushes that same token to 60%, the model has established a directional momentum in its reasoning.
Exactly. And auto-guidance just mathematically extrapolates that vector further. You can push the probability even higher without actually running a third or fourth loop.
That is so elegant. So it boosts the benchmark performance significantly without adding a single extra FLOP of compute overhead at test time.
You got it. You are just extrapolating the trajectory of the reasoning that the model has already computed.
That is just brilliant. You know, if we zoom out from the mechanics of MagicNorm and Logit lenses, the core takeaway for the ML engineering field here is profound.
It really is.
Because we have been trapped in this paradigm where cluster size and brute force token scaling were the only levers we were allowed to pull. And this paper kind of shatters that illusion.
Completely. Smart structural priors, like biological dual timescale recurrence, paired with targeted task completion objectives, can actually replace immense parameter counts.
The compute to performance frontier is just much more malleable than the massive lab suggest.
It is. And this research points toward an imminent future where we fundamentally decouple knowledge from reasoning.
Which is a huge shift.
Right. Because for the past 5 years, we have forced models to memorize the entire internet just so they could learn how to think along the way. But HRM-Text proves that a tiny 1 billion parameter core can handle highly complex mathematical reasoning natively on a $1,500 budget, entirely in its latent space.
So if you don't need parameters to store trivia, you only need parameters to think, which leaves you with a really provocative question. What happens when you take this highly efficient recurrent computational brain and hook it up to an external retrieved memory module or a dedicated factual store?
Yeah, it really makes you wonder.
Our monolithic trillion parameter transformers, just a clumsy brute force phase of AI development that we are about to age out of. It honestly forces you to look at massive server farms and wonder if they are actually necessary. Definitely something to explore on your own. Thanks for joining us for this deep dive into the source material, and we'll catch you next time.